So in this video, we're just going to summarize the periodic trends that we studied in this lesson. So here are the periodic trends all summarized in one spot in the periodic table. As you can see, remember the arrow means pointing towards the direction that it's increasing in. So electron affinity, ionization energy, and then also, or we're missing electronegativity here, electronegativity as well. They all increase from left to right, and they also all increase from bottom to the top. And the same thing applies to non-metallic character. Also increases from left to right and then towards the top. So really the only two that go in the opposite direction of that is your atomic radius. So atomic radius goes up from top to bottom and up from right to left. And same thing with metallic character. So basically, if you remember your atomic radius directions and your metallic character, then the other directions are essentially just the opposite of that. Remember that noble gases, they don't follow the electronegativity, nonmetallic, and electron affinity trends because they already have their full valence shell and they don't quite fit that mold or definition there. There's a great detailed summary you can view by clicking here. It's a nice little table that goes over all of the trends again and goes over the reasons for all those trends, so the atomic explanation, as well as the periodic table explanation as well. So you will be allowed to use your periodic table. You just need to remember what direction the trends are in. If you're making a reference sheet for an accommodation of some sort, it might be a good idea to just make a little mini periodic table like this and then put little arrows to summarize those trends. And maybe under those arrows, you can briefly explain why those trends exist, why they are, and maybe a little example as well. And so that'll help to organize this whole lesson into one little chart rather than, 2 or 3 pages. So just a couple little reminders before we do some practice problems, just to keep in mind as you review the trends. So remember ionization energy when you want to remove an electron that requires energy. Remember electron affinity when you want to add an electron, typically energy is released, and the more favorable it is, the more it wants to be added, the more energy will be released, the more negative that number is. Each electron shell or orbit takes up some space, so that explains that's why there's a larger atomic radius when there's more shells. Remember the period number is equal to the number of electron shells. Remember that the group number is equal to the number of valence electrons. And remember, when it comes to that effective nuclear charge, the reason there's an attraction between the protons and the electrons is because in the case of charges, the opposite charges attract each other. So positive attracts negative. So what we're going to do is we're going to do a couple practice problems related to this here, just to recap what we saw. They're in the handout over here. We can use our periodic table to answer these practice problems over here. So we'll start with question 1. Rank these by increasing atomic radius. So we want from smallest to biggest in terms of atomic radius. And we know atomic radius is larger towards the left than the bottom. So we have carbon, aluminum, oxygen, and potassium. Carbon, aluminum, oxygen, and potassium. So oxygen's smaller than carbon. We know that because carbon's more towards the left. So we know that for sure. And if we're comparing aluminum and carbon, aluminum would be larger because it's at the bottom and the left as well. So aluminum, carbon, and oxygen. So our smaller one is going to be oxygen, then carbon, then aluminum. But we need to check where potassium falls. So if we look at potassium's way over here. It's going to be larger because it's more towards the left and the bottom, so it's the largest one, even larger than aluminum is. So we'll make potassium our larger one. So oxygen is smaller than carbon, carbon smaller than aluminum, and aluminum smaller than potassium, with potassium winning in terms of the larger atomic radius there. Rank these by increasing electronegativity. So electronegativity, the trend is, if we're to add it, electronegativity trend is this way and this way, kind of like the ionization and electron affinity trends. So increasing means smallest to biggest. Remember that in terms of electronegativity, the noble gases don't really have a high electronegativity because they already have a full valence shell. So already I'm going to go and make that the smallest one. And then I need to compare all the other ones here. So I have oxygen, sulfur, and aluminum. I'm pretty sure aluminum is going to have a low electronegativity just because it's a metal. So aluminum's going to have a low electronegativity. So I'd say that's next in line for lowest. Now it's between oxygen and sulfur. So Oxygen's higher up than sulfur, so it's a higher electronegativity. So it's higher than sulfur. And just to confirm, aluminum is towards the left here of sulfur, so that means it has a lower electronegativity than sulfur. So we have aluminum, we have sulfur, and oxygen in that order there. What's the difference in electron affinity and ionization energy? Well, you can look this up in the notes, but the idea is that electron affinity is the energy released when you add an electron, and ionization energy is the energy required or put in to remove an electron. Trend-wise, though, they both follow the same trends on the periodic table, and you can explain why those trends are being followed as well. Why does F have a higher ionization energy than I? So F versus I, and you can look this up in your notes, but I'm going to explain it orally, and then you can write it out, and you can try to explain it orally as well. But we have F and I. Why is it that F has a higher ionization energy than I? Well, there's two ways I want you to explain this. First of all, look at the position. So the ionization energy increases as you go up in the periodic table. So fluorine is higher up than iodine. That's the first point, periodic table location point. Second point is fluorine has fewer shells, therefore less shielding, and holds on to its outer electrons more tightly, which means it requires more energy to remove those electrons. So that is explaining it in terms of the atomic structure. You could also explain it this way with atomic structure. Iodine has more shielding because there's more shells, and as a result does not hold on to its outer electrons as tightly, and it requires less energy to remove the electrons. So when you explain an answer like this, I'm not going to write the whole thing out. I want you to give 2 points. The periodic table location point and the atomic structure point. So this means the effective nuclear charge and the shielding idea. So both those points should be there when you're describing that. And then why do elements in the same family have similar properties? Well, that you can look up in your notes as well. But remember, same family refers to a same column, and you can describe this in a variety of ways. But the general idea is, what do they all really have in common in that column? They have the same number of valence electrons, and that's primarily what dictates why they have similar properties in those groups. You can also discuss other things. You can go deeper than that and discuss how they fall in similar locations on the periodic table, and therefore would have similar atomic radii compared to metals that are more to the right of them or to the left of them. They'd have similar ionization energies compared to elements that are to the right or to the left of them. So you can go and add even more a deeper amount of depth there, or a greater amount of depth there, because now you know more about these trends. But overall, it's really because they have the same number of valence electrons, and you could go and discuss the effective nuclear charge as well. One thing to mention as well here, I didn't make a mistake in the handout. This should be metallic trends. I did state it in the presentation well. It's just in the handout. It's a mistake over here. But I will fix that so you won't see it in the good copy of the handout when that occurs.